So, building on last lecture, we're doing of something very similar. So, you ran a two-group experiment. How do you make inferences about the population mean differences, which is what we're after? Well, today's discussion is about what do you do when you have a within subjects design. This is called a dependent samples t-test. When you have a between subjects design, you use the independent samples t-test. So, how do you know that you have dependent samples or a within subjects design? Well, if the same person is in both your control and your experimental groups or in both of your groups, then you know you have a dependent samples design. That's a fact. One of the most common ways is in a pre-post experiment. So before you just do something, after you do something, you measure something. So it's like baseline manipulation post baseline, right? That's a very common use for a within subjects design. Or let's say you have the same person, they participate in both of the conditions. Maybe, it's experimental and control, or maybe if you're doing research like I do, you're going to show them black and white targets and see how they respond. Essentially, this is what this is what we're used to. So this one isn't hard for us to miss. We have the same people in both conditions, then we know that our two samples are dependent or linked through that one person. Now, there are cases where you have different people in both of your conditions and you still have a within subject design. You have different people, but they are twins. One twin per condition. You have different people, but they are siblings. One sibling per condition. You have different people, but they are spouses. One spouse per condition, right? You have different people, but they were matched to have the same level of anxiety. That's the same thing. One matched person in each condition. The data in condition 1 is linked to the data in condition 2 through something about the participant. So then you use a dependent samples design. Today, I want to just focus you on the same stuff before. How would you analyze your data like a pro? How would you interpret your data like a pro? And how would you present your data like a pro? There is a new, slightly modified T formula that I'll show you, but essentially, let's get right to it and start some analysis. First thing, we got to get the numbers that we need for our analysis. So what are those numbers going to be? For the sake of parity across the two lectures, I'm going to use the same experimental design as I did in the previous lecture. Now, this is the one where I said, where common methods of discussing prejudice actually make people less likely to believe they have free will and prejudice. By telling people everyone is prejudiced, I believe you're going to reduce their free will. In comparison, my comparison group is telling folks that everyone can overcome their prejudice. Now, in today's example, I'm going to assume that one participant read both articles and provided their free will belief measures twice. Okay. So I think that's really, really important to understand. So essentially, that is the change I'm making today. So this data should look familiar to you. Now, it's not labeled in the way that maybe you see right away that it is beliefs in free will that are the numbers, but you can see that if you were paying along, you know that it's beliefs in free will over prejudice that are numbers in this data except for the new participant column. So I have a participant column that allows you to see the linkage. Participant 1, when they read that everyone is prejudiced condition, they reported their beliefs in free will to be a 3. When that same person read the Everyone Can Overcome Prejudice article, they gave us a 5. Participant 2, 2 and 3. Participant 3, 1 and 4. Those are beliefs in their own free will over their prejudice. And participant number 4 gave scores of 3 and 4 that are their beliefs in free will over their prejudice. So we're going to be calculating the same things we did last time. And we're going to have to enter this data into SPSS. So now we have the same calculation checklist. I want the means. I want the standard deviation. It will be Bessel corrected. I want the mean difference. I want the average standard deviation, which we know is now called our pooled standard deviation. We want our Cohen's d. We want our 95% confidence interval of mean difference. We want our 95% confidence interval of the Cohen's d. Those two provide truth. We want our t-statistic so that we can find the p-value. It's the same t-statistic as last time. The degrees of freedom and the p-value are what we need. So that's what we got. We are also using SPSS to calculate this, and like I said, the new version of SPSS gives these beautiful 95% confidence intervals of the mean difference and the 95% confidence interval of Cohen's d. If you have an older version, you're going to have to wait to the end of the lecture to learn how to use the Excel file to make your 95% confidence intervals. So what we're going to do is we're going to calculate those right now. All right, so we have our data presented right in front of us, and we need to figure out how to input it into SPSS. Now, my first thing, I don't start with the variable view. I start with the data view, and then I literally just enter in my data. So I want to just know this is participant 1, that their score on the everyone is prejudice condition was a 3, and that their score on the everyone can overcome is a 5. Now, remember what I said in the previous lecture. In SPSS, it is always one row for each participant in your study. So that's why I've added the participant column. So it's one row for each participant. That's what I just did. I entered the first participant. Now let me just click my variable view, participant, everyone is, and I'm going to call this one overcome. Going back to my data view, I'm not going to hit any value labels. Like everything is a numerical continuous scale variable. If you want to look back, I'll click on the variable view, right? Everything in here is scale. And even if it shows up as unknown, SPSS doesn't like freak out when it doesn't know the scale. It just assumes continuous. So now I have to continue this for participant 2, which is a 2 and a 3, participant 3, which is a 1 and a 4, participant 4, which is a 3 and a 4, right? Let's do our analysis. So analyze, compare means, because we're comparing means. So analyze, compare means. Analyze, compare means. I'm just trying to get some repetition in there. There's now a third word that means the same thing. So you got to within subjects design. You use a dependent samples t-test, which is also known as a paired samples t-test. So dependent samples, paired samples, and within subjects are all the same design names. I click that. It is really important to learn how to click in your particular answers in the right way. Now, variable 1 needs to be the condition that you expect to have the higher mean, like you're hypothesizing to have a higher mean. I really love this fact. I like to do all my analyses where positive t-scores and positive Cohen's d's mean that my hypothesis is supported. So I am throwing in overcome because I expect overcome to have a higher free will. So they go in first, right? It just saves me the headache of dealing with negative numbers, or at least gives me not the headache of dealing with negative numbers, but the headache of knowing that negative numbers in my data sets always goes against my hypothesis. And I expect the everyone is condition to have lower beliefs in free will, just like I talked about the previous time. Now, if you don't do this, if you put them in the other way, you're going to get a different t-test. This sort of setup. So I'm clicking on overcome because that's the one I predict to have the higher mean. Then I'm clicking on everyone is prejudice. That's the one I expect to have the second highest mean. Estimates of effect size. You definitely want to have this clicked. If you don't have this option, you have an older version, but your version's basically the same. And you want to make sure you have clicked on standard deviation of the difference. That's what we're using. That's what we're supposed to use for the Cohen's d here. So you just got to remember that. Make sure that first button is clicked. The other ones give you similar but different answers. Now I click OK. And what do you see? Well, you see my means are the same as they were in the previous example. My standard deviations are the same as they were in the previous example, so are my standard errors. Now you got a new measure, though. It's the correlation between the two free will measures and free will belief over prejudice scores. So scores in the everyone is condition are kind of correlated with scores in the everyone can overcome, but this is a non-significant correlation. If we look, we have my paired samples t-test. Well, it's not my mean, right? I really wish they didn't call it mean. That's not the mean. It's your mean difference. It's your standard deviation of the mean difference, your standard error of the mean difference, your 95% confidence interval of the difference. So that's truth, your t-value, degrees of freedom, your p-value. And then we got our Cohen's d. This is the standardizer. That's just our pooled standard deviation. We have our point estimate, and we have our 95% confidence interval from small to large, essentially. So you can see that we have everything we need right here. That's all. That's all we need to do. So now we have all our numbers. Let's do the same thing as we did last time. All right, so now we have to interpret our data. We care about two things. We do care about describing our sample statistics to other people. We care about our sample data, the data we collected. But if you look, and again, look at the font size, we care about finding truth more than anything else. And for us, finding truth is making inferences about the true population parameters. These are inferential statistics, inferring what the true population mean difference is in this specific test. All right, so now we're looking at our output. We want to look at our descriptive statistics. We can see our means are 4 and 2.25. Our number of observations per group is 4 and 4. Our standard deviations within each condition are presented right there. We know that our sampled mean difference is 1.75. We also know that our pooled standard deviation is at 0.957, and our Cohen's d is 1.828, which is a massively large Cohen's d. So I want to interpret my inferential statistics. I want to make inferences about truth, about the true population values that I'm interested in. So essentially what I need to do here is, first things, I'm going to look for my p-value. So I see my t-score, my degrees of freedom, my p-value is 0.035. What do I know from that? From that alone, I know that it's very unlikely that my true population mean difference is 0. So I'm going to say I've disproven statistically that my true population mean difference is 0. My true population mean difference is not 0. My p is less than 0.05. My true population mean difference is not 0. Now, those of you that like to be super technical sometimes, I don't know why, but sometimes we get in that mindset. Yes, there's a probability that we may be wrong and the null hypothesis may be true, but when our p-value is less than 0.05, we reject that null hypothesis. Reject it. Like, boom, I'm rejecting it. I'm saying it's not true. My true population mean difference is not 0. Then I got my 95% confidence interval of the mean difference. That true population mean difference very likely falls between 0.22 and 3.27 with some numbers after it. That interval, 95% of 95% confidence intervals, contain the true population value we seek. So we know that somewhere in the interval is the true population mean difference for our experiment that we are seeking. That's where truth lives. And then to interpret it, I love that SPSS is giving us 95% confidence intervals of the Cohen's d. When I look at this interval, I see what I saw before, right? I see that the true population mean difference could be a small mean difference of 0.10. Cohen's d of 0.10 is small. If 0.2 is small, 0.10 is tiny, right? All the way up to a massively large Cohen's d of 3.493. Remember, a large Cohen's d of 0.8, this is 3 times larger than a Cohen's d of 0.8, right? But essentially, what do we know? Well, number one, our true population mean difference is not 0. We've rejected the null hypothesis. True population mean difference is not 0. True population mean difference falls somewhere between 0.22 and 3.27. Worst case scenario, this is a tiny difference. Best case scenario, this is a massive difference. Could be a medium difference. These are all in line with my hypotheses. You can see that because the Cohen's d is positive. The mean difference is positive, and everything's in line with my hypothesis. But essentially, this is the data we seek. Now I know truth. So then you have to present your data. I'm going to let the lab focus on graphs. I'm going to focus on writing up your data. This is not complicated. We don't need a t-test graph, essentially. So what do we want to report in our results? We want the means and standard deviations. Always, 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 for every condition, means and standard deviations. That's necessary for future meta-analysis. We want our p-value. We know that. We'll get to that in a second. We need our t and the degrees of freedom to go with our p-value. The p-value is just simply telling the readers, if we've disproved the null hypothesis, that your population mean difference equals 0. You include your 95% confidence interval of the mean difference because this likely contains the true mean difference of the population. So that's truth. 95% of 95% confidence intervals contain the true mean difference that we are seeking, the population mean difference that we are seeking, the truth that we want. We then include the 95% confidence interval of the Cohen's d because this is the only way we can really understand our 95% confidence interval of the mean difference. Do you have a precise estimate of truth? Do you have bad science? Do you have a useful effect? All these questions can be answered by converting to the 95% confidence interval of Cohen's d. So we definitely want that. Again, on punctuating statistics, we use parentheses to enclose statistical values. You can see that in this example right below. Use parentheses to enclose degrees of freedom. So every t you write should have a t in parentheses degrees of freedom equals whatever the t is. Notice also the spacing, right? You definitely have spacing between the equal signs. Take that look out. Use brackets to enclose limits of confidence intervals. So here's an example, right? They have confidence intervals presented. Use italics for statistical symbols. That means italicize T, F, P, N, degrees of freedom, italicize, all that stuff if you're putting degrees of freedom in there. And use an italicized lowercase n to refer to your sample, to a sample of the population. So that means your sample size. This is important. If a value has the potential to exceed 1, use the leading 0. If it does not, like our p-values, you do not use leading zeros. You've seen this before, but if you want to write these things out, you can see Cohen's d's, plural, singular plural is abbreviations, written out, symbols, singular and plural. You know, this is now in 2 of my slides. Go ahead and pause here. Take a shot of this, but really p-values and Cohen's d's and t-statistics, t-values, t's and t's. Those are really the only ones we're talking about thus far. So just wanted you to know what those were. All right, so I know a lot of folks like the rules of how to write an APA and all that. So let's just show how I would present this finding. You can copy my sentence directly. I'm trying to present all my statistics in one sentence. Reading the everyone can overcome their prejudice articles statistically increase beliefs in free will over prejudice in comparison to the same individuals reading the everyone is prejudice article. Some things I want to point out. Statistically increased is my way of saying statistically significant. I don't use the word significant. You can use it there. Led to a statistically significant increase in beliefs in free will over prejudice, if you wanted to alter that. But that's number 1. Number 2, notice I wrote in comparison to the same individuals reading the Everyone is Prejudice article. So in case somebody isn't reading my methods, I'm clearly stating this is a within subjects study, so that in case somebody misses that, maybe a reviewer, whatever. And then look at how I present my data. I just put all my data in there. The data only has one interpretation. So I have my mean and my standard deviation for group 2. I have my t-statistic. Notice that t-statistic is italicized. In parentheses, I have my degrees of freedom. I have a space. I have an equal sign. I have a space. That's my t-value, comma, space, p, space, equals, space, point. I don't have a 0 before it because p's cannot be larger than 1. 0.035. semicolon, D equals, space, 1.83, comma, space, 95%, space, CI, space, bracket, 0.10, because Cohen's D's can be larger than 1, comma, space, 3.49, bracket, semicolon, mean difference equals 1.75, comma, space, 95% confidence interval, space, bracket, 0.23, comma, 3 space, 3.27, bracket, comma. That's how you do it. That's how you get it all in there. That's how you follow the rules from the previous section. The one thing that isn't italicized is CI, or 95% CI, mean, standard deviations, t-scores, p-values, d-scores, all those are italicized. Then sentence 2 plus, because it's more than one, clearly, right? I would like you to include discussion of what you found, particularly in relation to the population mean difference and the population mean difference, essentially. So these results indicate that messages suggesting everyone is prejudiced reduce beliefs in free will over their prejudice in comparison to messages suggesting everyone can overcome their prejudice. The p-value suggests that the true population mean difference is unlikely to be 0. However, the 95% confidence interval suggests that the true population effect size is likely to fall between a small effect with very little impact and a large effect with tremendous potential for changing these beliefs. While we are actively attempting to improve our methods to reduce noise and error with the hopes of providing a more precise estimate, activists and educators should refrain from applying this intervention in the real world. This may only lead to the tiniest gains in belief in free will over one's prejudice. That's the exact same that I had before. What I think is important for you to understand is that just write these in first person. When they're not your data, that's fine, but you will never be asked to write a paper in third person about somebody else's data. So always, every example, write it like it was your own. So there's only a few new concepts. The formula for the dependent samples t-test, I want to show you that. And I want to show you degrees of freedom for the dependent samples t-test. But I do want to say this. What do you really need to know? You don't need to know what follows here. You need to know how to do everything I just did when you have a dependent samples t-test. You need to be able to do that. You also need to know when you have a dependent samples versus independent samples t-test. Are my samples connected? Are they linked through the participant some way? Pre-matched, siblings, same participant, right? You always got to look out for that. But I'm going to go ahead and talk about these concepts so that you can see what's going on. But I just want to warn you that what comes after this part is not essential. What that means is it's nerd thoughts. It's there for thinking. It's there to expand your knowledge. But if you are lost on the first part, just analyzing your data, interpreting it, I'd rather you go back and watch that part of the video again. So this is a choice. Go back, rewatch that video, or watch the nerd thoughts, or skip to the end and do the homework. The nerd thoughts are really for those of us that want to think about stats at a higher level, that want to challenge sort of our conceptions of it, that want us to really grasp and understand like the foundational principles or what's going on. In terms of what we need to know how to do, you've already learned that. So nerd thoughts are next. Your choice whether or not to engage. But if they're too much for you, you don't need to understand what I'm saying from this point forward. So this point forward is for math nerds and for you to really get a handle of what's going on with the basic calculations if you want. But if you want to just interpret data, understand it, be a good scientist, you shouldn't be doing these by hand. You should be doing them with the computer. So let me go into the hand calculations real quick, and I'll show you what's different. So first thing, conceptually, the t-statistic formula is the exact same for conceptually. It's the sampled mean difference minus the mean difference if the null were true divided by standard error. So it's very similar to a Cohen's d of our sampled mean difference in comparison to the null mean difference. I have not taken the null mean difference out of here. The mean difference if the null were true or the null mean difference is 0. We know that. It gets dropped in a lot of calculations. But what you're looking at is a difference between your sampled mean difference and the proposed mean difference divided by the standard error. So it's very similar. And standard error is the standard deviation of that distribution of all possible mean differences if the null were true. So if the null were true, our sampled mean difference is t standard error is different from the proposed population mean difference of 0. So that's the basic idea. That's the basic formula of a t calculation. It's very similar to a Cohen's d, but it's a little different. I'm going to get into those differences in the next couple of slides. First thing, though, before I show you how the calculation formula has changed for the t-distribution, you have to understand what a difference score is. D means difference score. So twin 1 minus twin 2 equals a difference score. Pre-post equals a difference score. Brian in the experimental condition minus Brian in the control condition equals a difference score. The dependent samples t-test is calculated from different scores, which it's pretty easy to do this t-test by hand. Let me show you another property of difference scores. So the sampled mean difference equals the mean of the difference scores. I just want to demonstrate this to you with very simple numbers. Let's say we had two groups, score 1 and score 2. Not two groups, but each participant took 2 scores. Score 1 and score 2, they're right there. Right? Well, if you look at score 1, whatever that was, let's say it was pre, you have 1, 2, 3, 4, 5. Well, the mean of those numbers is 3. I chose them so they were easy to have a mean. And the scores of the second scores are 2, 4, 6, 8, and 10. And the mean of those scores, chosen to be just as easy in terms of calculating the mean, is 6. So our mean difference is 3 minus 6, which is negative 3. Now, if I calculate the difference scores, right, you're going to see that the mean of the difference scores also equals negative 3. So 1 minus 2 is negative 1, 2 minus 4 is negative 2, 3 minus 6 is negative 3, 4 minus 8 is negative 4, and 5 minus 10 is negative 5. So the average of negative 1, negative 3, negative 2, negative 3, negative 4, negative 5 is negative 3, which is also the sampled mean difference. I'm just showing you that the average of the difference scores is the same thing as the sampled mean difference. That's important because of the formula that's next. So t-statistic, the idea, same thing, right? Like our sampled mean difference minus the mean difference if the null were true divided by standard error, except now our sampled mean difference is represented by the average of the difference scores, which is the same thing. So in the second equation, I've blown up the standard error. So the mean of the difference scores minus the mean difference if the null were true divided by standard deviation of the difference scores divided by the square root of n of the difference scores. So now in the next equation, I'm just getting rid of the 0. I want you to know it's there, but the average of the difference scores minus 0 divided by the standard deviation of the difference scores divided by the square root of n. I've just gotten rid of the mean difference if the null were true. We know that simplifies to 0. In the next equation, it's going to be gone. So now my t equals the average of the difference scores divided by the standard deviation of the difference scores divided by the square root of n of the difference scores. Well, that again is Cohen's d divided by 1 over the square root of n of the different scores, the number of different scores. N of the different scores is the number of different scores. You can do my same calculation trick. We can see here that if I take t times 1 over the square root of n, that's going to equal Cohen's d. All I'm doing is taking that both sides of this equation and multiplying them by 1 over the square root of n, right? T times 1 over the square root of n equals Cohen's d. So I just flipped it. Also, that looks a little different from the one we looked last time. The one we looked at last time said Cohen's d equals t times the square root of 1 over the n that we were interested in. Well, that actually works out just fine here as well. So basically, this is the same. Both of these equations work exactly the same. You can mess around with them by hand if you'd like. But I want to show you my calculation trick still works. And why do I think this is important? Because oftentimes you get the t, you get the number of different scores, but you don't get the Cohen's d. And for me, it's really hard to interpret data without the 95% confidence intervals. But when I don't even have the Cohen's d, the basic point estimate of Cohen's d, it's really hard for me to interpret an effect from a study. So ultimately, this will come in handy. But you can see this is how you calculate the t-score. I'm going to go into it a little bit, what it is. Let's do the calculation for this problem together really quickly. So participant number one, my everyone is prejudice group. My everyone can overcome prejudice group. That's my original data. I've just added to this data. Now, first thing I did was calculate my D-score. Now, I didn't just calculate everyone is prejudice minus everyone can overcome. I calculated it the other way because what am I predicting? I'm predicting that everyone can overcome prejudice article will increase beliefs in free will over prejudice. So I took 5 minus 3 to get 2, 3 minus 2 to get 1, 4 minus 1 to get 3, 4 minus 3 to get 1. Okay, so those are my difference scores. What's the average of my difference scores? 2 plus 1 is 3, plus 3 is 6, plus 1 is 7, divided by 4. There's 4 different scores equals 1.75. You'll remember from last time or from our output that is the mean difference. So then I calculate my deviation scores: 2 minus 1.75, 1 minus 1.75, 3 minus 1.75, 1 minus 1.75. I get a couple negative, a couple positive deviation scores. Right? The next thing I do is I square all those deviation scores to get rid of the negative sign. Squaring them leads to the numbers you see right there: 0.06, 0.56, 1.56, 0.5625. I didn't read all the numbers, but you can see them right in front of you. First thing to do, my sum of squares, calculate my sum of the squared deviation scores, 2.75. I just added all 4 of those numbers up. My next step, I want to calculate variance. Well, variance is sum squares divided by degrees of freedom, or n minus 1. So in this case, 2.75 divided by 3. There's 4 different scores minus 1. I'll explain that to you in a second. But our variance is 0.92. Well, standard deviation is represented by the symbol s. Variance is represented by the symbol s squared. We take the square root of variance to get our standard deviation. And in this time, the square root of 0.92 is 0.96. Check it on your calculators. You'll see that weird things happen when you do squares and square roots of decimals. Then the last column, I'm just like, okay, how do I calculate my t-score? Well, my t-score is my mean difference divided by standard error, or my average difference score divided by standard error. They're the same thing. So here, mean difference or my average difference score is 1.75. My standard deviation is 0.96. My n is 4. My standard error equals standard deviation divided by the square root of n. So my standard error equals 0.48. So my t-score equals 1.75 divided by 0.48. So my t-score equals 3.67. That is or 65. That is the exact t-score we calculated from SPSS. And that's how you do it. But why would you do this? How many errors could you make in this process? Right? Definitely doing it by hand doesn't make that much sense, but I want to show you where it's coming from. So what is the t-statistic conceptually? Well, let's look at the formula. It's just the sampled mean difference, which is equivalent to the sample mean of the difference scores. I'm not going to say that again, but sampled mean difference is what I'm going to talk about, minus the null mean difference. So if we want to disprove the null, we know we have to have a sample mean difference that is drastically different than the predicted mean difference if the null were true. We divide that difference in our sampled mean difference minus the mean difference if the null were true, divided by our standard error. And it's standard error where we got to really figure out what that is to understand what the t-statistic is doing. So we already know that if we sampled a large mean difference, we're getting closer to disproving the null, but we don't know on average what mean difference we would sample if the null were true. Well, that's where standard error comes in. Standard error is a standard deviation. Standard deviation is average error. And this specific standard deviation is telling us, on average, if the null hypothesis were true, sampled mean differences will differ from 0 by whatever our standard error is. So if let's say our standard error was 2, on average, like if that were our standard error, on average, we will sample a mean difference of 2 when the true mean difference is 0 quite frequently. On average, we will sample a mean difference of 2 when the true mean difference is 0. That's how you start to think about standard error. It's like, okay, I want to compare my mean difference to the standard error, and I want my mean difference to be drastically different than standard error, because standard error is the average or expected mean difference that we are going to sample if the null hypothesis is true. On average, we have error in our sampling mean differences when the null hypothesis is true. So if we want to disprove the null hypothesis, we got to show that our sampled mean difference is drastically different than our standard error. So let's look at an example. Let's say our t-score is 1 and our mean difference and standard error were both 2. So what do we know about standard error? On average, if the null were true, we would sample a mean difference of 2. Like on average, we will do that, right? So us sampling a mean difference of 2 doesn't mean anything. So in order for us to disprove the null hypothesis, what we have to sample are mean differences that are drastically different from standard error, often 2 or 3 times greater than standard error. So that's all it is. If it doesn't make sense, you know what, and you want to understand it, we can talk about it in office hours. If you don't want to understand it, very few people think about what this actually means, but now you know. Degrees of freedom, you got to remember, we do not have 8 individual scores. We have 4 pairs of scores. Thus, we have 4 different scores. We have 1 mean of the 4 different scores. And so instead of 2 means, we have 1 mean. Instead of 8 scores, we have 4 scores. So imagine that we didn't know the individual scores, but we knew the mean of these 4 scores. And this mean had to still be the mean. How many scores are free to vary? Well, 3 can be any number. The 4th has to be a specific number so that the mean of the different scores stays the same. Let me show you in the next slide, okay? And this is just my riddle, right? How many scores, in this case different scores, are free to be anything and still have the same mean, and how many of them are fixed? The free ones are degrees of freedom. Let me show you. So here's our data, 2, 1, 3, 1. These are our different scores calculated earlier. We know that our mean of the different scores is 1.75. Imagine that all we knew was the mean. So we had x scores that averaged to 1.75. How many of these scores are free to be anything, and how many of them are fixed? Well, I'm still on the Jordan kick, so I chose 23, 23, 23. Right? I could have chose any number, but I chose 23. Those 3 are free to vary. That last one, negative 62, has to be negative 62 in order for the average to still equal 1.75. So you want to analyze these 3 data sets. For each data set, I want your final write-up in your SPSS output. Patient happiness before and after new therapy. What do we expect? We expect that patients are happier after a new therapy than before. The order of numbers in this data set equals the same person. So the first observation in the first data set is the first observation, is the same person as the first observation in the second data set. Participant 2 is the second observation, participant 3, 4, and 5. 6 ODHA treated rats. Those are rats that have like a rat model of Parkinson. We're looking at their maze speed in seconds before and after a new Parkinson's drug. So their speed of completing the maze before the drug was 60 seconds, 75 seconds, 90 seconds. Their speed after is 10, 20, and 50. Now we are expecting speed to go down, right? That's what we are hypothesizing. The drug should make speed go down. That's just what we would expect. A Parkinson's drug is going to increase the ability to complete a maze for these rats. So the ability to complete the maze means less time spent in the maze. And then for extroversion, twins extroversion, there's no hypothesis here. I have no prediction here. We are technically predicting a null difference essentially, but this is one where you're really going to want that 95% confidence interval, the mean difference, to help you interpret it. So ultimately, run these 3 data sets, analyze them. That's all we need to do. All right, those of you that have an older version of SPSS, what you need to do is you need to use the Excel file that is uploaded to our course website. What you will notice, is this a t-test? Yes. That's where you start on the red, right? Yes, it is. Is the comparison between dependent samples? Yes. Before we said no. Now we go here. Do we have the mean, standard deviations, correlation, and n? Yes, we do. So it's telling you numbers of pairs. So we know we got 4 numbers of pairs, right? If you look back at our output, our correlation was 0.426. 0.426. So now I plug that right here. 0.426. Mean 1, mean 2, standard deviation 1, standard deviation 2. I can easily go back and get that. 4 and 2.25, those are my two means. So 4 and 2.25. If the mean you want to be subtracted, like the larger mean, the mean you expected to be larger, should be put in the mean 1 condition. Standard deviation 1, standard deviation 2. When we get back to our data, what do we got there? 0.82, 0.96, 0.82, 0.96, 0.82, 0.96. I'm going to double check, make sure those are paired up. 0.82, 0.96 are paired up with the larger and smaller. So right here, right now, with everything being reported, we have our Cohen's d of 1.82, and we have a 95% confidence interval with a Cohen's d of 0.46 to 6.82. Now, if you're looking at the video and like these aren't the same, yeah, they're not the same. SPSS is using a better version, a better way to calculate these 95% confidence intervals. But ultimately, here we go. We have what we need. We have what we want, and everything is very good with that. That's good enough. There's different ways to calculate it, but don't let that get you down. But that's your answer, and there you go. That's how you calculate it.